So in section 112, we talked about this yesterday when we gathered. They're talking domain. They want to know what the domain is. And so if I'm looking at the domain, I'm concerned about three things. I'm concerned about, is there a denominator? I'm concerned about, is there an even root? And is there a logarithm? And if there's one of those three things, then we have to deal with it. And the way we deal with it, and we talked about it again yesterday, is for denominators, set them equal to 0. Domains, everything but that, because you can't have a 0 denominator. If you have an even root, it has to stay positive, so you make it greater than or equal to 0. And if it's a logarithm, it has to stay positive and can't equal 0. So similarly to the even roots, it's just going to be a greater than 0. It's not going to be an equal to. We did the first couple examples. I think we were up to example 4, and that's where I'm going to start today. So here's example 4 coming at you. These are a little tricky with the logarithms. I mean, you know the deal. The deal with logarithms, the beginning concept is not tricky. You know that x over x minus 4, whatever comes after the logarithm, has to be greater than 0. Like, that's not rocket science from what the notes were, right? Except the story is, you can't have, first of all, you can't have the 0 denominator. So you've got to keep whatever's in the logarithm positive, but you also have to keep x minus 4, the denominator. You can't have a 0 denominator. So x can't equal 4. If it did, you'd have a 0 denominator. So there's a couple things going on in this guy. This part here, this x over x minus 4, is the part that you have to kind of put your thinking cap on. Because if you have a fraction, and you're thinking fractions, I'll come down here, the only way I can have a positive, right, I need to be greater than 0, the only way I can have a positive value is if I have a positive over a positive in my fraction, or if I have a negative over a negative. Both of those situations are going to be things that cause a positive fraction. And so you have to think about what numbers are going to work in this to keep it where it's positive over positive. So let's think about it for a minute. If I have, say I have a 3 in here. I'm just picking numbers. If I have a 3 in here, 3 is going to be positive over a negative. That won't work, right? So if I pick, what if I pick 5? 5 over 5 minus 4 is 1. 5, that's going to be positive. So 5 works. Well, let's go backwards a little bit. Will 4 work?
No.
But how about 4.5?
Yep.
Yeah, right? So you see, you end up having to kind of play games with this a little bit, and you can see that you're going to end up with values where you need them to be x is greater than 4. It can't be equal to 4, right, because that would cause the 0 denominator, but it can be greater than 4. It could be 10, it could be anything bigger than 4. Now let's talk going the other way. We said it can't be 3. We said, how about 0? Would 0 work? 0 would give you 0, wouldn't it? And it can't equal 0, so we don't have that. It can't be 0. How about negative 1? Ooh, negative 1 over negative 5 is positive 1/5. That's going to be a value that works, right? So negative 1 is going to be part of something that works. How about negative 0.5? Negative 0.5 over negative 4.5. That's going to be a value that works as well. So what do you think this inequality is going to be?
Less than 0.
Good, less than 0. Exactly right. Now that's kind of complicated because you really need to put your thinking cap on to really play all the games with that. All right, so let's see if we can put our domain together. We've got, because that's what the question was asking, we know we have x values have to be greater than 4. We know we have x values that have to be less than 0. And we know that x can't equal 4. They were our 3 pieces. Well, x can't equal 4 I can actually ignore because it's not even part of my inequality anyway. So that right there is your domain. All right, last one, before this is still on the video stuff. Where's the function continuous? And so if I look over here at the inequalities, it tells me the areas where I'm concerned about. So places that I'm concerned about are when x equals 0 and x equals 3. Those are places I'm concerned about. But I also have to look and see at the functions that I've got involved. If I look at these functions I have involved, this guy's got a denominator. This one has a 1/7, but it's not a denominator that has a variable in it. So this one, the domain would be all real numbers. This guy, I know that x can't equal 7 because x equals 7, I would have a 0 denominator. And the last one, the bottom one, I know that x can't equal, think about this, 4x minus 20. So my x would have to be 5, right? If it were 5, I'd have a 0 denominator. All right, so then let's investigate it a little bit. Could we put it all in one equality? Yeah, absolutely. She's talking about number 4 with my domain being greater than 4 and less than 0. You could put that into a combined statement, yeah. Yep, you can definitely do that. All right, so over here, I'm going to check to see if it's continuous at 0. Do you remember how to do that? You got to take those two equations and what do you do with them? Do you remember? Maybe not. Set them equal to one another? Right? Because in order for them to be continuous, they'd have to be combined. They'd have to meet up at that location, wherever that location is. So we're looking at taking the first equation and setting it equal to the second equation. And now algebraically, here was my first thought when I was looking at this question. My first thought was to algebraically solve that, right? And I started looking at that going, ooh, that's really ugly. Is there a better way that I can check this thing out where I don't have to go and do that? Because think about it, you'd have to like cross multiply, you get into cubes, and then you've got to solve for x. Oh my goodness. It would get messy, really messy. So I'm only concerned about what it's doing at 0. I don't care what it's doing anywhere else. So all I really need to do is plug a 0 in for my x's and see what happens. So if 0 is my location I'm concerned about, I'm going to have a 0 minus 2 times 0 minus a 1/7. So on the left I get a 1/7, negative. And on the right I get a 3 over 0 minus 7. I'm going to put a little note here of what I did. I plugged in x equals 0, and that's where I'm getting these numbers from. This one would give me a 3 over negative 7. Well, that means that as I come at 0 from one side, I get negative 1/7. As I come at 0 from the other side, I get a negative 3/7. I guess it should be this way. It's going to be lower, right? So I end up with it not connecting. It's a disconnected thing. So since these are not equal to one another, you know that this is a discontinuity. It's discontinuous at x equals 0. Okay, then I'm going to go over here and figure out what it's doing at 3. So, doing the same thing, but now I'm using the bottom two equations because they're the ones that involve the 3. So I want to know, is 3 over x minus 7 equal to 7x minus 15 over 4x minus 20? And the number I'm concerned about is the 3. So I'm going to let my x's be 3 and see what happens. So if I let my x be 3, I have 3 over 3 minus 7 is negative 3/4. If I let x equal 3 on the other side, I get 21 minus 15, so that's 6. And if I put a 3 in here, I have 12 minus 20. That gives me a negative 8. Are they equal to one another? Well, 6/8, right? If you reduce it, 2 goes into those. So there's my negative 3/4. So this place, it's continuous at x equals 3. All right. So if I'm looking at where this thing, I know it's discontinuous at 0. And I know that if I look at these values over here, I have to come back to the discontinuities I had from the beginning. And I'm thinking about this thing. It's a little tricky, but watch the numbers they say. If I have x is less than or equal to 0, that goes to negative infinity. So this one, it goes to negative infinity on the left. And it also has values between 0 and 3. And it also has values. Why did they take the 7 away? He said the 7 wasn't in the domain. And I'm trying to figure out why at the moment, why he said that. Any thoughts? I'm coming up with my domain. It's all real numbers, but x can't equal 0. That was my discontinuity here. It can't equal 5. And he said it can equal 7. The 7 wasn't in the domain, so you didn't have to include it. But I don't see how it's eliminated, frankly. Thoughts on my kid's part?
Wait, so why can't it equal 5?
It can equal 5 from back here.
Oh, right.
Right, from these, like if I look at the equations I was given, it can't equal 7 from this guy because that would be your 0 denominator. It can't be 5 for this guy.
Oh, they said that the equation that you get the 7 from has restrictions of 0 to 3.
Oh, thank you. That's where it was. Hannah got me. Okay.
That was
So,
Jenna, I read it up there.
was it Jenna? They can see, my kitties can see your chat when you chat in. I have the big screen with what you're seeing. Okay. Yeah, if I look at this, 7 isn't in this domain. That's what it is. Thank you. So you can ignore the 7. That's why the 7 was not included. Thank you, thank you. That's it. All right, so the domain is actually just all real numbers, but x can't be 0 or 5. Okay, that took care of the video notes. Let's see if we can pick some of these to do in the practice. Number 5 was my first pick. Number 5. And then we're going to do 7 and 10.
I was wondering, do you want us to write it that way that I did? That was like the coordinate u to the other coordinate.
Okay, so Hannah's asking if we go back to if we go back to looking at these, some of them he wrote in interval notation with unions. I think the inequality is just as good. I mean, either one is correct, so whatever you're more comfortable with would be my answer. You can write them either way, but I think most times what we're going to see with these is it's easier just to leave it in its inequality form. And do we have to list the domain when the question only asks for where it's continuous? They're kind of one and the same thing. Asking where it's continuous and asking what the domain is. So I guess if I were to answer that specifically, just make sure you're answering the question. So if you're saying where it's continuous, you can just answer where it's continuous if that's what the question's asking. The domain kind of says the same thing, but just in a different way. All right, number 5, find the domain. Question number 1, remember there's 3 issues: denominators, even roots, and ln's, logarithms, okay? So you're looking to see if you have any of those things. And obviously you've got a denominator. Denominator can't be 0. You're going to figure out what causes the 0. So you're going to take t squared minus 2t minus 48, set it equal to 0, factor it. Lucky for us it does. What, 8 and 6? So t equals 8 and t equals negative 6 are going to give you 0 denominators. That's what it can't be. But I also have a root. So I'm going down my list. Denominators number 1, roots next thing to come 2, and you know that whatever's inside the root, t minus 1, has to be greater than or equal to 0. It has to stay positive. All right, so t is greater than or equal to 1 when I solve that. And then I need to merge it all together, take my information and put it together. I know that t is greater than or equal to 1. You start with the inequality. But then go back up to these guys. If I'm on a number line and I start at 1, will I hit 8? Right? I will, because I'm going to the right. So I have to include that. T can't equal 8. And then I'm going to the second thing that I said I couldn't have, which is a -6. If I'm 1 and greater than 1, am I ever going to hit -6? And the answer is no, so I can totally ignore this piece. This piece is ignorable. Is that a word? Where's my word wall? I haven't even decorated. You should see my classroom looks so sad.
More decorated than one
Is it? My, well, probably just because of the tattoos and things that I got all over the walls. But with my foot being so out of commission, I didn't want to climb on chairs and put up bulletin boards. I was like, this just isn't happening at the moment. Plus, you kids weren't here until just now, so we'll figure it out. I need helpers. I need little elves to come and decorate my room.
I'm not good at that.
Yeah. All right. Next one's number 7. Because number 7, one of those goofy things you got to think about where it's positive and negative. So first thing I can see from number 7 is that I know I can't have a 0 denominator. So I know that x minus 10, if I set that equal to 0, I get x equals positive 10 is what it can't be, right? It can't be that. So first thing is denominator, I know it can't be 10. Second thing is I know my fraction has to stay positive. I know that x over x minus 10 has to remain greater than 0. So if I start thinking about numbers in here, right, like we did the last time, you know that the only way it's going to be positive is if I have a positive over a positive or a negative over a negative. So if I pick a number, pick any number, how about 5? I pick 5. 5 over 5 minus 10 gives me a positive over a negative. That's not going to work. So 5 doesn't work. How about, you can kind of tell when you start looking at this, what other numbers do you think you might want to try?
So that's be greater than 10 to make it positive.
Yeah, so think about 10. Like 10, don't you, like if you look at the equation, you can think maybe 10 might be an interesting number to think about. If I'm a little bit close to, say I'm 11. 11 over 1 is positive. That works. How about 10.5? 10.5 would still give me positive over positive. So you're exactly right. 10 is one of those places you want to look. It kind of gives it away if you think about it. So I know that these values have to be t, or it's x's. X has to be greater than 10. If x is greater than 10, I have a positive positive.
Less than 0.
And Hannah's guess is less than 0 for the other part of it. So let's think if that works. X is less than 0. We said 5 didn't work, right? We tried 5, that didn't work. If I try 1, that's not going to work, positive over negative. But if I try negative 1, negative 1 is going to be negative 1 over negative 11. Negative over negative, there's positive. And so yeah, 0. If I use negative 0.5, that's going to work. So it's kind of a thinking game, but they kind of give you some ideas of the numbers you want to try from the equation that you have. All right, well, x can't be 10. Well, it can't be 10 anyway. So this part of it doesn't really matter. You can ignore that. But you've got x is greater than 10 and x is 0. That's your domain for this guy. All right, last one from this section. We have x plus 8. This is number 10. And on the bottom, I have an x squared plus 8x. Well, if I think factoring, my x plus 8 on top stays the way it is. I can factor out an x on the bottom. And I know my denominator can't equal 0. So my denominator has 2 pieces. I know that it can't equal 0 from the x that's factored out. I know that x plus 8 can't equal 0. So x can't equal a negative 8. Going down your list, do you have even roots? You do not. Do you have logarithms? You do not. So that's really it. All your deal is for this one, the domain, is going to be all real numbers, but it can't equal 0 or -8. Number 11, there's a question on, sure. Okay, so number 11. This one has, if I go down my list, it doesn't have the denominator, I don't worry about that, but it does have a root. So one of the things I know is that x minus 7 has to be greater than or equal to 0. That's your rule for even roots. Well, that gives you x is greater than or equal to 7. But then if you remember the logarithm rule, because it is a logarithm as well, it's a natural log there, so you know that this has to be not only greater than, it's only greater than 0, not greater than or equal to 0. So how is that going to change up? And this is because of the ln, you have to do this, it's going to change up this inequality only to be that x is greater than 7, because remember it can't equal 0. And so that's your story with, because of the ln, you take away that equal to sign. Any others that you look at that scare you? Okay, cool. That's the end of 112. Let's talk 113. Okay, here comes 13. All right, so this one's talking, it's kind of similar to the last section. Each section, it seems like they're kind of very closely related. In this one, it's talking about removing discontinuities. How do you remove a discontinuity? And it's all about holes, if you remember holes. So holes come around when you factor and a group cancels. So back in pre-calc, I know we talked about that. And in my margin, the big thing that I put out there is that you got to factor. Don't forget to factor. That's one of the very first things you want to do. And removable discontinuities are ones where there's a hole. Holes happen when you've got factor groups that cancel. And so what they're saying is that when you have a removable discontinuity, the limit exists, but it doesn't equal where the hole is. So the limit would be a yes, I got a limit, but it doesn't have the same value as what the coordinate is. All right, that's the math concept behind this. And so, again, this was from the video. He factored x squared minus 1, x minus 1's cancel, that creates a hole. Find the value of the hole, here it is, x minus 1, whatever that common group is, equals 0, so x equals 1. And then he came over here and he said, all right, well, what's the corresponding y value? Well, the corresponding y value is whatever the limit is. So the limit as x approaches 1, I'm left with this equation, x plus 1, because remember these canceled. And so if I plug a 1 into this, 1 plus 1 is 2. Look at that calculus. And so you have a hole at the coordinate 1, 2. And so that was the first one that he did on the video. Second one. If you need me to go slower, you just holla. Second one says if the function is continuous for all real numbers, when x equals -4, what's the value of -4? And so you go through and you take the function, get rid of the hole, and now I have my function is x plus 2. If my function's x plus 2 and I take the limit, plug in a -4, then my value is a -2. So the hole is at -4, -2, and that means that that's where their coordinate is. So f of -4 is a -2. So same thing goes, factor, cancel, you're left with a new function. Use that new function to plug in the value you're looking at. The x value is -4. Negative 4 plus 2 gives you negative 2. That tells you the coordinate. So f of negative 4 is negative 2. All right, last one like this. You've got now a piecewise function. They want to know what's the value of a that's going to cause this to be continuous at 6. So it's the same kind of setup. You take your function, you factor it, cancel out, and create the new function. The new function is just an x plus 3. Set that equal. For these to be continuous, they have to have the same value. So set them equal to one another, solve it out, and that's the a value that would cause this to be continuous. So they were the quick examples from the video. Questions from video stuff before we try a few? All right, so let me go to practice problems. Let's do number 2. We'll do number 2 first. Okay, so number 2 says, if the function is continuous for all real numbers when x equals negative 10, what's f of negative 10? Well, this is exactly the same question like number 2 was up above from the video. And so I'm going to do the same thing I did there. I'm going to take and factor it first. So I'm taking my function, f of x. I'm going to factor it. They multiply to 20 and add to negative 20 and add to 8. I'm going with x plus 10 and x minus 2. Again, use the denominator as a hint. You kind of know it's going to maybe factor into that group, right? So use the pieces they give you. All right, take away the whole. Remove the discontinuity. So I have a new function, and my new function is just x minus 2. So the question's asking you, what is f of negative 10? Well, that's going to equal negative 10 minus 2, or negative 12. There it is. That's number 2. Next one, let's look at number 6. I'm trying to pick a little bit of this and a little bit of that. Number 6. This one's a little bit of a different question. This one says, okay, here's your piecewise function. What's the value of b that's going to make this continuous at x equals 7? This is kind of like that last question from the video. But if I look at this guy, I'm taking and factoring the function that I have. So I have x squared minus 16x plus 63. I want to factor that. One of the groupings is probably going to be an x minus 7, right? So if I factor it, I get x minus 7, and I get an x minus 9 to get my signs to go correctly. And so I cancel my whole, get rid of the discontinuity, and my new function is x minus 9. So I take that. I know that x minus 9 has to equal b, the other equation I have, in order for it to be continuous. They have to have the same y value. And I'm looking at that and I'm going, whoa, I got 2 different variables. They got to give me some kind of information to make that better. And so I know the x value when x is 7. So I'm going to plug that in. 7 minus 9 is what b would have to be to make this continuous. I solve it out. I get a negative 2 for b. And I be finitoed. All right, then he kind of makes things a little more complicated down here towards the bottom with values like number 9. Number 9 is another one. So we just did 6. I want to look at 9. Do you see how 9's got a little bit more beef to it here? You got a crazier function, and you've got a b that's in the first function as well. So it looks a little different than the one that we just did. So if I look at this one, again, it comes down to factoring. I've got x squared plus 5x plus 4. Well, that becomes x plus 4, x plus 1. And on the bottom, I have a b and an x plus 1. All right, so take away the whole, remove the discontinuity, the topic of this section. And so now I have x plus 4 over b has to equal b, the other equation, the second equation there. You can plug in the x. What's the x value we're concerned about? We're concerned about where x is 1. This seems odd, though, to me in a sense, because I think it's a typo on their part. This should be a negative 1. See how these are negative 1s? They have a typo there. This should be a negative 1 as well. All right. So if I look at this, that's going to give me negative 1 plus 4 over b equals b. Or negative, or positive 3, I should say. 3 over b equals b. Now, how do you solve that? Any thoughts? Cross multiply, multiply by b? Yeah, both are great answers, right? So however you're thinking about it, I know I tend to be a cross multiplier person, and since you've been in my care for all these years, you probably think of that too. But multiplying by b is good also. So cross multiply, you end up with b squared equals 3. But I don't want b squared, so square rooties come into the party. Here's square rooty. I get b equals plus or minus the square root of 3. So they're done quite the same way as the ones we did up in number 6. Just the equations are a little bigger, and you've got an extra variable involved. You'll see that with number 10 as well. All right. Then we're going to flip to the next page. We're going to pick one more. All right. 11 or 12. Let's go 12 looks worse, so we'll pick 12. Okay. If I'm looking at number 12 for this guy, I've got another piecewise function, and the idea is the same, right? I have to take 5 sine of 3x over 4x, and I want to figure out where that equals b. Now this one can't be done just the same algebraic way. I need to bring limits into this thing to be able to solve this out. So here's what I'm going to do. I'm going to change this into the limit as x approaches my number is 0. I can tell that from all of my parts over here. And it's going to be the limit for this thing of this 5 over 5 sine of 3x over 4x. And whatever that limit comes out to be is what b is. Now, you're probably looking at that going, So, you need to go back about, I don't know, to section 1.9 or something like that. It was back in the day. There was a rule, and the rule said this. The limit as x approaches, let me move this over so you can see me, x approaches 0 for the sine of x over x equals 1. Very good. Okay, now we're going to use this rule on this problem, because remember the rule still applies with numbers in front of the x. So this one has a 3x. Well, that means I need to make it look like a sine of 3x over 3x. To be able to apply that rule, right? It can be whatever number it wants to be, but it just has to be the same number on the top as the number on the bottom. So I'm going to separate this whole thing out. I'm going to separate it out so that I get the limit as x approaches 0. The 5 I can't do anything with. I know I have to have the sine of 3x, and I also have a 4x. Now watch how I'm going to do this. I'm going to put, remember I need to have the x on the denominator there. And that means that this would be a 4 over here. I could have put the 4 over here, below the 5. Now I'm going to stop for a second and let you think about that. Did I just do a valid math move? Or the math police going to come and take me away? I haven't changed anything, right? I just changed where they're located. So I have a 5, I got the 5. I got the sine of 3x, I got that. I have a 4 and an x on the bottom. I'm good to go. But the reason I separated it is because remember, to make this rule work, there has to be a 3 here. Well, I can't just magically throw a 3 in there. Wish I could. Can't do that, right? Can't just throw the 3 in there. So how can I compensate for that so that I don't change the value of the fraction? Multiply it by 3. So we want to put a 3 somewhere else on the top. 3 over 3 is 1. That makes it now a valid math move. I haven't done anything to change the value of that fraction. I've just multiplied it by 3 over 3. Let's apply limits. If I plug a 0 in, right, there's nothing to plug it into, it's just a 5. We know that this rule from over here is equal to 1. And then the last fraction is actually a 3/4. And so that's going to give me, when I put it all together, an answer of 15/4. How about that? That one was a little tricky, right? Bringing back in some stuff that we had from previous. Okay, so take a look at section 113 and tell me if there are any others that you would like for me to do before we talk 14. I'm looking, I got a whole lot of nothing. All right, we'll look at 14. Do you guys at home need a minute to copy it? Because we didn't really think we were going to do that today.
I don't have it.
I think did I give it to, were you here when I gave out the?
I don't think you will.
Yeah. Okay, so yes, Chloe needs a minute. So we'll take like a 3-minute break so you can copy and print it out if you need to. We're going on to 114 and I'll be right back because I'm going to give Griffin a copy.
Thank you.
You're welcome.
Miss One, are we allowed to use the courtyard still?
Yeah, the courtyard, my understanding is you can go through the courtyard. Yeah. They have not closed that off. I know they've got all these crazy ups and downs. You can only go in certain places and crazy. And going to the bathroom now is all on those e-passes.
Yeah.
So you got to e-pass it up.
I'm just gonna hold it.
I agree with you. I do agree with you.
If I can. Okay.
All right, let me ask this question too in the chat. Have you watched the 114 video? I did not ask you to, so you did not have to. But yeses or nos, did you watch the 114 video? It's just going to tell me how fast or slow I need to go. Okay. I'm seeing lots of no's. That's fine. All right, let's talk a little bit about vertical asymptotes, the old vase, right? From back in the day. And if you think about vertical asymptotes where they happen, what part of the equation are you looking at when you're concerned about a vertical asymptote?
Denominator?
The denominator. Good, good, good. Okay. The denominator determines where you have a vertical asymptote, And it also determines where you have a hole. The whole last section was all about holes. It was all about removable discontinuities, which are holes. But what happens when you have stuff left in your denominator that creates now a vertical asymptote? And so, here's the big concept. Are you ready? If you're a vertical asymptote, number one, you can never cross a vertical asymptote. You can cross horizontals, you can't cross verticals. So think about it if you're driving. If you're driving in your car and you come up to this vertical asymptote, right? You've got two choices. You're either going left or right. You're going either towards negative infinity or you're going towards positive infinity. You don't have any choices. So the answer for the limit on either side of a vertical asymptote has to be either positive infinity or negative infinity because it can't go through it. Okay? So that's kind of the idea that you're thinking about for these things. One of the first things, I'm going to put this in my margin, one of the first things you want to think about is you want to factor if you can factor. Again, that's very significant over these last couple sections. And what I just said is what I put in my margin note as well. I said that when you approach a vertical asymptote, when you approach a VA, the y values go to either positive or negative infinity. You don't have any other choice. You're at a dead-end road. You got to go right or left. All right. So when you approach a vertical asymptote, the y values go either to positive infinity or negative infinity. So the first question says, use this equation and find the vertical asymptotes. Well, factoring is going to be our friend. So let's factor the top and the bottom for our function for number one. All right, you have 8, so it's going to be x plus 4, x minus 2. Bottom is going to be 4 and negative 3. And I look at this and I say, okay, I have a hole at x equals negative 4. They didn't ask me for that, but I know I do because they cancel. But I'm left with x minus 2 over x minus 3. It's the denominator that determines the vertical asymptote. So if you have things that have not canceled out and you're left with something in the denominator, that's the guy that is going to create your vertical asymptote. So in our case, it's x minus 3. Where that equals 0 is going to be my vertical asymptote. Okay, so if it cancels, that's a hole. What you're left with creates the vertical asymptote. And then you get to numbers 2 and 3, and he actually gave you a little picture of what this looks like. So here's the graph. Let me show you the graph. Draw it up here. The graph kind of goes like this. And if I look at that, I can see that there's a vertical asymptote in this neighborhood. And I'll make it up here so that this is where x equals 3. Kind of makes sense, right? Got a vertical asymptote. So the question says, what's the limit for number 2 as x approaches 3 from the left for this function? And we say, what is it?
From the left?
Yeah.
Negative.
You're right. Yes, negative infinity is the answer. Very good. Okay. Now we're going to do the same thing. We're going to use the picture and we're going to try this number 3. The limit as x approaches 3 from the right, that's coming this way. Come from the right, it's going to positive infinity. And then he went on to ask the question, what's the limit as x approaches 3 itself? Does not exist. Very good. Right, because it's doing two different things, right? It's not merging at the same y value. That's right. So you got it doesn't exist. But this limit stuff is confirming that you really do have a vertical asymptote there, because remember, when you're taking the limit of these things, it's either going to positive infinity or negative infinity. If your answer is positive infinity or negative infinity, it's confirming that that's going to be a vertical asymptote. Okay, then number 4, find the limit. It says actually find the limit, and this is kind of weird, but find the limit as you come at 3 from the right. Well, you know that if you go to 3 itself, if you go to 3, it's going to be a zero denominator. You can't do that. And you have no algebraic manipulation you can do to this fraction to make it any better. So back in the previous units that we did all sorts of algebra games to make it so that you could actually evaluate it. This one, there's no algebra games to play. So what you have to do when you have a situation like that is just pick a number that would be in the neighborhood of to the right of 3. Now think of it, if you're at 3 on the number line and I go a little bit to the right, I'm going to use 3.001. Right? I can pick whatever I want, but this is the number that he picked on the video, so I'll go with it. And all you do is put it in there, direct substitution. So if I'm plugging this in, I'm doing a 1 minus 3.001 over 3.001 minus 3. And so, hey, how are you? I'm good. Now, kids, this is all about positive and negatives. I don't care what the number is, necessarily. I'm just concerned about, because what do you know is happening at 3 itself?
It does not exist.
It doesn't exist. That's where your vertical asymptote is. You know you have a vertical asymptote at x equals 3, because that's your denominator that would cause the 0. Now, if I'm coming out of vertical asymptote, what are my answers for the limits? It's either positive infinity or negative infinity. You need to know which one it is. And so here, all you need to do is figure out, is this going to be positive or negative? Because it's all going to be infinity. The answer is going to be infinity. All right, so I have 1 minus 3 on top-ish, right? Negative on top. And I have 3, a little bigger than 3 minus 3 on the bottom. That's a positive. So I get a negative, I get a negative, over a positive, which means I have negative infinity, and that's my answer. So the question, if I want to be really mathematical and wonderful here, if I take the limit as x approaches 3 from the right of 1 minus x over x minus 3, I get negative infinity. And we're going to do the same type of thing over here in number 5. But number 5, before I get into this, I can factor that bottom a little bit. And you'll see why that's going to be a friend to you as we try to do these. So x minus 3, and I have an x minus 1 and an x minus 1. Well, what happens when x is 1? If I try direct substitution, because that's always the first thing you want to try with these, I get a 0 denominator, correct. So I end up with a 0 denominator. If I have a 0 denominator, what do I have? A vertical asymptote. Where is it? At x equals 1, right? So I've got a vertical asymptote at x equals 1. And they want to know what's the limit as I come to 1. My answer either is positive infinity or negative infinity, because that's what happens around a vertical asymptote. So I need to figure out what it's doing to the left and to the right. The limit as x approaches 1 from the left, I'm going to call it f of x. And I want to know what the limit's doing as I come at 1 from the right for my function. And then I can figure out what the actual limit is as x approaches 1 itself for this function. You see what I got going on there? I got all 3 pieces. I need to know what it's doing to the left. I need to know what it's doing to the right. All right, there's our setup. And so I'm looking at the next piece of this. If I come at 1 from the left, if I'm at 1 on a number line, and I'm just to the left of that, 0.9, right. So I'm going to use 0.999. 0.999 minus 3 over 0.999 minus 1. I can square that, right? I've got 2 of that grouping. You could write it out twice, whatever you want to do. And again, it's all about positive and negatives. Up top, 0.999 minus 3 is going to be a negative value. And the bottom's kind of nice because I don't even have, if you think about it, when you square something, your answer is always going to be positive. So this does actually come out to be negative, and a negative squared is positive. There it is. So my answer for this guy is negative infinity.
This is winner.
Hey, you're on my side of the world. It is so good to see you. You are out of area.
Well, it's Gator Hour, so I'm trying to teach kids to get them caught up on stuff. You know what I mean? It's like,
yeah.
But then I'm working more harder than
Tell.
just turn yourself in. Oh, this is a good class.
Oh, these guys are awesome. Yeah.
I know these guys. These guys are.
These are. I got it good over here.
Yeah, good seeing you.
You too. Mr. Coveley just came by and said hi. Hi, kids. All right. So now I'm going from the right. What's right of 1? What would you use? 1.001. Yeah. Minus 3 over 1.001 minus 1 squared. All right, well, up top, I'm still getting a negative. Down the bottom, because I'm squaring it, I got a positive, and so I get a negative infinity. Well, guess what? Because these are both going in the same direction around that vertical asymptote, then the limit at 1 is going to be negative infinity. If one was positive infinity and one was negative infinity, you would have doesn't exist because it's going in 2 different directions. But because on either side it's going in the same direction, you're going to say that it's got that negative infinity. All right, that's vertical asymptotes. We good? We'll try some practice. We are going to pick, let's go with number 5 for our first one. Number 5. Job number 1 is to factor. Okay, so you're going to factor this guy. This one's going to take a little doing because in the top, actually in both top and bottom, you can take an X out. So you guys take a second, factor, and we'll see if we match. Alrighty, so you've got x plus 6, x minus 4 on top, x and x minus 1 on the bottom. X is canceled. There's a hole when x equals 0. So my new function that I'm using is this right here, and the question is identify the vertical asymptote. Well, the vertical asymptote comes from the denominator, and so I set the denominator, x minus 1 equal to 0, and it tells me where my va is, x is 1. I also want to look at number 6 right next to it, because number 6 is kind of interesting. I can factor the top. That's an AC method thing, so take a second and factor that top. Okay, so you got a 7x minus 3 on the top and an x plus 1, and a 7x minus 3 on the bottom. So your 7x minus 3's canceled, they become a whole. And the question's asking you what's the va. And you say, there is none. You're right, there is none. Is there a denominator left? There's not. So you don't care, right? So you don't care what the numerator is. So this one has no va. No va. Anybody applying there? Villanova? Anybody? Any kids? I applied there and I didn't get in. They didn't want me.
It's so expensive.
It is really expensive. Yeah, that was my number one pick and they didn't want me. I survived. It's okay.
Where did you go?
Funny enough, I started out at St. Joe's in Philly.
Really?
Yeah, but I wanted to be a doctor, a pediatrician. So that lasted all of about one semester. There were a lot of reasons that I had a really sleazy roommate. She used to like tie stuff on the doorknob so I knew not to come in. And I was having trouble in a biology class, and I went to the professor and I said, what are your office hours so I can get extra help? And he said, I don't do office hours. That's your problem. And then I was coming home every weekend because my grandfather lived with my parents, and he had Alzheimer's disease, and they couldn't go out even to the grocery store without somebody being home. So put all those things together. I was also volunteering at an elementary school locally I loved the kids in the elementary school. They were so cute, and like when they cut the light bulb moment happened for them, it was the coolest thing to me. So I was like, I'll teach. And so I came back home and I lived at home, and I went to now Rowan, back in the day at Glassboro State.
My grandma used to work there.
Yeah.
Counselor,
Yeah. So yeah, I lasted one semester at St. Joe's and then came back and went to Glassboro State. And I became a math teacher because I had horrible math teachers. Nobody I said, somebody's got to be able to do this and make it fun and make sense. So here I am 25 years later, 26 years later. All right. My life story. Here we go. Can we get let's go for number 7. Ooh, do you see number 7? Number 7 might make you want to cry when you look at it. All right, we're talking vertical asymptotes, right? We're talking denominators. Do you have a denominator? You don't have a denominator. Can you turn it into a denominator? Yep, you can. Okay, so that's what we're going to do. So I'm going to change this guy, and I'm going to make him 1 over the sine of 2x. Now I got a fraction. Now I got a denominator. And what do you know about the denominator to find a vertical asymptote? That denominator, it can't be 0. So you're going to figure out what's going to cause it to be 0. All right, so you have to go back and think about, and we've got in the classroom, we've got our unit circle on the wall here. I want to know, where is the sine of x equal to 0? At what locations? So that sine is the y value. If I'm around the unit circle, what y value gives you a 0? First.
Pardon the interruption. A reminder to please wipe down your desk and area before leaving class today. Once again, a reminder to please wipe down your desk and area before leaving class. Thank you.
All right, we who are here are helping you out. I'm looking around at my unit circle in the back, and it happens at 0, at pi, and at 2 pi, and I could keep going at 3 pi, 4 pi, 5 pi, whatever. So now, that's not what I have, though. I have 2x. So 2x has to get set equal to these things. And then I'm going to solve that for x. So this one becomes, if I divide by 2, 0 divided by 2 is still 0. This guy divided by 2 is a pi over 2. And the last one, it gives me a pi. Am I in the domain they gave me? Yep, between 0 and pi. All right. The rest of these are all figuring out, evaluating the limit. These are all, we don't have time to get into these, but these are all the ones where you're going to pick a number. Like this one, number 9, you would pick 1.001. You want something to the right of 1, and you're going to find the limit for that using a number to the right or left of the value they give you. So I think you have enough of a foundation to be able to finish those out without me giving you more examples. But holla if you have trouble.
What time is this class
It is over in 3 minutes, but you need to wipe your desks down. So we're going to make 112, 113, and 114 all due for Sunday. So you've got a couple days to do that. And I would recommend watching the videos for 15 and 16 because when we get together again on Monday, we can go through those two sections. And that'll give us a day to review, which is actually pretty good. So you're turning in 12, 13, 14 by Sunday, and then watching the videos for 15 and 16 before class on Monday. Does that make sense? All right. See you guys. Have a good day.
Is that okay then? No.
We have a quiz in Mr. Rose's.
What?
That's the job interview quiz.
You have to wear these gloves.
No, you don't have to wear the gloves. See the bucket? There should be things sticking out of the bucket.
Interesting.
They're your, yeah, and then there's hand sanitizer if you want it, but.
I feel like when this is all done, like, say we get the cure, everybody's gonna be like so much more clean, I feel like.
I think it's going to change. There's a lot of things I think are going to change. I think that people working virtually is going to be different.
Mhm.
I think that
I feel like it's better.
eventually it might get back to not being so clean because when the flu first came out, like in the 19 whatevers, I'm sure they were all protected and whatever, and then it got to the point where we were like
I know.
not.
Yeah. But I mean, I'm like so much more aware of like
Well, yeah.
stuff
Yeah.
I touch, you know,
Yeah.
just like realizing, like, say you go to Wawa, like, man, how many people are touching this?
Even like the dollar bills and like, oh
Yeah,
gosh,
like the money
oh
sign.
I never
Lord.
put cash in, like, at all.
Yeah.
You know, we never used to think about that at all.
Mhm.
Or even like going to, like, if you go to the
Mr. Kelly.
Eagles game or something like that, like having
Oh.
people on top of you, all over you.
Yeah.
Like we never
It
thought
was,
about
like,
that.
So close and personal.
It was, but
Other than
yeah, I don't think we're going to be quite so comfortable with that for a while.
Yeah.
I'll go